Okay, so we are going to be looking at Module 6 today. Module 6 is going to focus on, as we can see here, it's going to be CAM design and kinematics, okay? So you'll notice here that we have kind of our standard format or the way that our module is set up. We've got the learning plan, session recordings, as well as practice problems and the assignment. So as we look at our learning plan, you're going to notice that we have a PowerPoint presentation. I will be following along with this. We're going to be looking at chapter 9 in our textbook, okay? And you'll notice that we'll have session recordings here. I'll be adding the session recordings that we have for the lectures that we're planning on doing for this module. I'm planning on two. The first part we're going to be going over today, which is going to be what we call displacement diagrams. And the next time the next time we're together, we'll look at constructing the CAM profile. Then you're going to notice that we have some practice problems. So today we're going to be looking at the practice problems. I think might be all three. I forget if we're doing two of the three or all three. I forget exactly where these are placed. But we have a couple example problems that you'll be following along with and then submitting. Oh, just as a reminder, there are two questions here. Make sure you let me know two things that you learned and then also two things that you still need practice on or more or less. And then assignment number 6. Assignment number 6, there are just 4 problems, but you'll notice that they're worth 20 points each. So there is some steps that we end up doing there. So I used to have students say, oh boy, if there's only a couple problems, that means they might be long. They might be kind of long, okay? That's okay. But it's going to reflect portions of everything that we're learning here in our learning plan. So let's go back to our learning plan and open up that PowerPoint presentation. Chapter 9 in your textbook is starts on page 223. And then we'll kind of be going back and forth here. So objectives of this module are going to be to, first of all, identify different types of CAMs and followers. Understand the benefits and different follower motion schemes that there are, and there are a number of them. So we'll be looking at a couple in detail. Then I want you to have the opportunity to construct a CAM follower displacement diagram based on whatever type of follower motion is identified. And then lastly, we're going to construct the profile of a disk cam using a displacement diagram. Okay. So those are the things that we're going to be doing. So first of all, in the introduction here, we're going to just kind of talk about cams, like where are they used? Well, cams accept and impart motion. Cams are considered if you would, the input of the motion, and then a follower is going to have the resultant motion or the output. So it's kind of like if you have a cam, you have to have a follower. So there's actually two elements that you have to be concerned about in the arrangement of a cam or in the function of a cam. So if we look at a very common application in an engine valve train, there is a nice little simplified diagram here of how a camshaft is used. So what we have here is we have a valve engine train. You'll notice that we have the valve, okay? And then we have the valve spring. We have the stem of the valve that is then in contact with what would be the rocker arm. And then we have the cam shaft right here that has the lobe on it, okay? And this is where the actual cam is occurring, okay? I'll just wait. I just want to make sure that I have everybody's attention because we're focusing on Module 6 right now. You might have other things that you could be working on either in this class or other classes, but my expectation is that when we are in lecture and I'm going through things, I'm going through them for your benefit. Sometimes I get questions in lab that I feel are asked by people who aren't paying attention, okay? So please be on task with what we're doing right here. There isn't a reason to be on your computer typing anything in at the moment. Okay, so please follow along. So we've got a camshaft here. Now, this portion that has that elongated lobe on it, that is considered the cam itself, okay? We're going to be looking at what we call plate cams, and then they're going to be on a shaft. The shaft is going to rotate about a center right here. But as this rotates around, you're going to notice that that cam profile is going to be in contact with the rocker arm, which is what we call the cam follower. that cam follower always has to be in contact with the profile of the actual cam shaft here. All right. And to do that, you'll notice that we impart the use of a spring. The spring makes sure that this is always going to be in contact. Okay. And as this goes around, you're going to notice that if you can kind of picture this, the lobe comes around, this rocker arm is going to go down. And as that rocker goes down, it's going to push the valve stem down, which is then going to move the valve, up and down. Cams are going to be important for timing, okay? So we're going to find that we're going to be interested in what's happening on a revolution. What is motion that we need in one revolution of that cam? And then depending on how much time that we need to impart that motion, we're going to be able to determine exactly how fast that needs to be rotating or what its angular velocity will be for that cam shaft, okay? So, so there's kind of a lot going on here, but relatively simple, if you would, arrangement and design. Okay. So a cam can impart a very distinct motion onto a follower. So as we look, there's going to be things that are going to be called rises, falls, and dwells. Okay. And how they rise and how they fall is going to be important. And there's going to be what we call different motion schemes that derive how that's going to happen. And that's where the design process comes in. They're used to obtain unusual or irregular motion that would otherwise be kind of difficult to do. Okay. It's very simple to rotate a shaft around, have that lobe on the cam that is then just going to move something up and down rather than having to program it, use an air cylinder. And then there's a lot of other parts that are involved. So it becomes a very cost-effective way of getting kind of intricate motion or unusual motion that you might need for a particular function. Cams are used a lot in factory automation because they sequence displacements, those up and downs, and in, like we said, a very cost-effective manner. Now, there are different types of cams, and we'll see various types of cams on the top of page 9, or on the top of page 224 in figure 9.2. Okay, so what each one of these cams have is a place where it's going to involve interacting with a shaft. And then you'll also notice the cutout in most cases that has a key. The key is going to ensure that the cam is rotating at the same RPM as the shaft itself. Okay, so you can see a couple different arrangements, and really all that the arrangements that we have here are the profile around where the shaft is going to interact with the cam is just going to be a design of the motion that needs to occur with the follower. Now we also see a couple other types of cams down below. So the first one is going to be the plate cam, which is similar to the one that we saw above. Here again, here's the center line of where the rotation of the shaft would be. The key that's going through there is going to keep that cam rotating at the same RPM as the shaft. And then you're going to notice that we have another one. This is called a cylinder cam on the right-hand side. You're going to see here that the cylinder is going to be rotating, okay? And there's a groove that is going to be on the perimeter of it. And then the follower is going to be in that groove. And you're going to notice that this follower is going to go in and out based on following that groove, okay? And then lastly, we have a linear cam, because you're going to notice here that the cam is going to go back and forth horizontally. And then because of the pin in the groove here, the follower is going to go up and down. The arrangement that we're going to focus on for the work that we're going to be doing is going to be a plate cam with a follower. Okay. And it's going to be this arrangement here in part A of that figure. Now, as there are different types of cams, plate cam, cylinder cam, and linear cam, there are different types of followers as well as different shapes of followers, okay? So if I go underneath over here, you're going to notice that in figure 9.4, just over to the right, we have a couple of these different types of followers. The first one is going to be the knife edge follower. That's the type of the follower. And in addition, this knife edge, if we look at the center line of it, it is in line with the center line of where the rotation of the shaft would be. Okay, so that's called an inline follower, and the type of follower is going to be a knife edge. The next one that we have here is going to be a pivoting roller follower. And the roller just is going to, talk about how and the shape of the follower as it interacts with the cam itself. So here's that knife edge, just really comes to a point, and then you have the roller. The next one that we see down here is going to be, this is going to be a flat face. So here we have, as you can see, just a flat follower, but it's also considered offset because you're going to notice that the direction of motion here, which is vertical for that flat face follower, if we take its center line, we'll notice that there is a distance between the center line of rotation for the cam. So that's considered offset. So in line would be here where the follower motion is in line with the rotation of the center of the shaft. And then here we have offset is going to be where it's offset. And then lastly, we have a spherical end that is also going to be a pivoting. And again, it's just the type of interaction that it has with the profile of the cam. So a lot of different arrangements, and they can be in combination. You could have an inline with a roller follower. So there could be a roller on here. And actually, that's going to be the type that you're going to be designing for your assignment. Okay. You could also have an offset with a roller on it and or any combination here that we see. Okay. Now, follower motion, okay, follower motion. There are different types of motion here. There's translating motion, and then there's swinging or pivoting, which we've seen examples of. So translating motion or straight line is going to be the, in that very same figure, it's going to be the inline knife edge and the offset flat face. And again, what that says is the output motion. So the input motion is always going to be what the cam does. And the cam is a plate cam is always going to be rotating, always. Okay. So if the cam is rotating the input, the output is going to be in this case, this is the inline knife edge. The output is going to be, this is going to move up and down. Okay. And it's going to be linear or translating. This could be positioned, on the side or on the bottom, but it happens to be above. And it just means that we're taking an input of rotational motion and the output now is going to be translating or straight line. Same thing down here, even though we don't have the center lines in line with one another and the center line is offset, you're going to notice that as we rotate this, our input, the output is going to be linear. The other type, which is going to be pivoting, you're going to notice that as we rotate, this is going to, technically move up and down, but there's a center of rotation here. So it's actually going to pivot around an arc, okay, which center is going to be over here at that pivot point, okay? And we have that same thing happening, whether it's a roller or in this case, the spherical face follower, okay? So swinging or pivoting. Now, we already talked about the follower motion or the follower position. It is either going to be inline or offset for the reasons that we saw earlier. So again, just reviewing that, inline is where the translating motion here is going to be in line. If we extend it, it's going to go through the center of rotation of the cam. If we extend it here, it's going to be offset from the rotation of the cam. All right. Then we talked about, we've seen follower shape, the knife edge follower. Couple of things here. First of all, it is the simplest form because it just comes to a point at the bottom and you get point contact with the cam itself. But because of that, there are going to be high contact stresses. There's going to be it's going to wear rapidly. So not only is it probably going to dull, kind of like a pencil, if you would, on the end, but it's also probably going to dig in one area around the cam itself. And they're not really used all that much, especially for the reasons that are above here. The roller is probably one of the most popular It needs to remain in constant contact with the cam itself, as do all followers, quite honestly. Otherwise it's not following what it's supposed to. So there, like we see that there's means of keeping it in contact. It is the most commonly used, and friction and contact and contact stresses are minimized because of the fact that most often, if we look at a roller underneath here, a lot of times it's going to incorporate like a ball bearing on there. And so ball bearings are going to be lubricated. There's going to be very little resistance to rotating. So they have a lot less friction that they have to overcome. Oopsie. Sorry. Wrong thing. All right. But they do have the tendency to jam sometimes if there's steep displacements. So we try to not have, when we say steep displacements, meaning that depending on the ratio of the time to do the displacement to how much displacement you're going to do, if it needs to be really a large displacement in a short amount of time, they can jam. Okay. So you just got to be aware of that. The other types of follower shape here that we saw were the flat face. This can take those steep cam displacements without jamming. Okay. They can encounter, or they can use quick motions with those. They do have higher friction forces for the obvious reasons. And then deflections and misalignment can cause some high stresses as well. And then lastly, we've got that spherical phased follower. It can be used on the steep cam displacements without jamming. The radius compensates for what possible deflection could occur like on a flat face. But again, it isn't rotating like the roller, so that the frictions are going to be higher, in the case of these as well. So prescribed motion. So as we look at prescribed motion, as we said earlier, cams is going to be based on when we have a cam arrangement, it's going to be based on timing. And we look at what has to happen on one revolution of that cam. So the total amount of time that's required for a complete cycle or a complete revolution is going to be the total TI. I'm not sure why they use I, but they do. That's the total amount of time for one cycle or revolution is going to be equal to the amount of time that we need for the first motion plus the amount of time we need for the second motion, third, fourth, however many there might be. The ones that you're going to be doing for your assignment and for our examples are going to involve 3, 4, motions, and that'll be about it. So not super complicated. Now, we also need to calculate the required angular speed, W, the angular velocity that cam needs to rotate. So we're going to determine that by, okay, we have one revolution of our cam, which is going to include all the motion that is required, and the total time from right above here, the total time that we need for that. So we are going to be finding out what the angular velocity is for that shaft. So then we can make sure that we rotate it at the proper RPMs. So we're going to be figuring out that in RPMs, and then our total time is normally in seconds, like what happens in one revolution. So we'll be probably having to do a little bit of converting as we look at these problems. The last thing that we need to calculate, is it the last? Yeah, the last thing we need to calculate that is going to come into play when we're starting our and figuring out our motions here is going to be the beta, okay? And what this means is this is how many degrees is each one of those individual motions taking of one revolution around that cam. So we are going to take the W and we're going to multiply it by whatever the time was on top here. So you'll get that opportunity. So we're going to have, for instance, a beta for the first time interval, a beta for the second, a beta for the third, because then it tells us how many degrees of revolution do we need for each one of those, okay? And ultimately, as you can imagine, when we add up all the betas, they have to be one revolution or 360 degrees, okay? So kind of talked a little bit here. So let's start looking at our first example. Our first example is going to be found on page 226. It's example 1. And we're going to be looking at this together. So if we look at the problem statement itself right here, okay, problem 9.1, I'll zoom in a little bit. All right. It says that we have a cam. It's supposed to be used for a platform that will repeatedly lift boxes from a lower conveyor to an upper conveyor. This machine is shown in the figure right here down below, okay? Plot a displacement diagram and determine the required speed of the cam when the follower motion sequence is as follows, okay? So you're gonna notice that here's the sequence. It's 5 steps. It says we want to rise 2 inches in 1.2 seconds. We want to dwell for 0.3 seconds. And then we want to fall 1 inch in 0.9 seconds, and then dwell for 0.6 seconds. And then lastly, we're going to fall an inch in 0.9 seconds. Okay, so that's the motion we want in 1 revolution. Okay, so our task then is we're going to determine the speed of the cam when the follower motion identified in that problem is going to be what we use. And we also want to identify and understand the essential parts of a displacement diagram. So we won't be able to plot this displacement diagram at this time, but we're going to be looking at the elements of it and what is needed, okay? So let's take a peek at what we have here. So step number 1, and we will follow this example along, and this is one of your practice problems, so you want to get out a piece of paper and label it example 9.1. You don't need to draw this diagram here, okay? So example 9.1. So they gave us the motion that we need to impart. Now remember, for the cam, this is everything that has to happen in 1 revolution, and this is the sequence, okay? So the first step, second step, and so on, okay? And how much time is associated with each one. So you'll notice here that the first thing they want us to do is they want us to determine what is the total time in a full cycle. A full cycle is 1 revolution. So the total time is going to be adding up each one of these, okay? So to show that, so this is going to be step number 1, okay? Our total time. So we need to identify this as capital epsilon, capital T sub I. Again, I don't know what the sub I is for, but it's what they use for total time. Is going to be equal to, now it's going to, we're going to have as many times as steps in our motion that is required. So it looks like, we look directly above, there are 1, 2, 3, 4, 5 steps. I mean, they're identified there. They're numbered as 5. So I'm going to have a T1 plus a T2 plus a T3 plus a T4 plus a T5, okay? So my total time, my T1, if we look, the time is going to be how much time we have to rise those 2 inches. That's going to be 1.2. Our T2 is going to be 0.3, and so on for each one of these. So T1 is going to be equal to 1.2 seconds plus 0.3 seconds plus 0.9 seconds plus 0.6 seconds plus 0.9 seconds, okay? So my total time all the way around, what do we get for the value here? So 1 revolution of our cam, how much time? Adding each one of those up. 3.9 seconds. And I think that agrees with what's there, right? So this is going to be one of our values that we're going to be using. So it takes 3.9 seconds to go around 1 revolution to accomplish this task of 5 sequences of motion. Okay. Then step number 2, we want to determine what is the rotational speed of our cam. Okay. So that means that we're going to be figuring out what is the rotational speed of our cam. Remember, the rotational speed of the cam is our input motion, okay? Now, we know that we need to make 1 revolution per, now, typically we're going to be in a revolution per the amount of time, right? So the time for 1 revolution is actually, we should write this in variable form first. Going to be the summation of the TIs, right? So we're going to stick with 1 revolution on the top per, and this is going to be 3.9 seconds, okay? 3.9 seconds, because that's how much we have for one revolution in a cycle, right? So the W of my cam is going to be what? If I take 1 divided by 3.9. And I'll pull out the chat box if anyone virtually would like to chime in. Put it over here. 0.2564. 0.2564, and that's going to be revolutions per second, right? Thank you for the confirmation, Ben. So that's going to be revolutions per second. Okay. Now that one's going to come in handy for our calculations going forward, but as we know, a lot of times we want to report our angular velocity in RPMs. So you're going to notice that they take the next step and they convert this to revolutions per minute. So I've got my revolutions already, but I know that there are 60 seconds in 1 minute, right? I want to get the minutes on the bottom. So then that means that my W of my cam can also be expressed as how many revolutions per minute? 15.38. And that would be RPMs, okay? So this would be the answer to the question. We would be reporting out like what will be the angular velocity of our cam, okay? And that was part of the question. So it said, what is plot the displacement diagram and determine the required speed of the cam. So this is the required speed of our cam. Now what we need to do is we need to plot, we're going to look at how they plotted the displacement diagram. Now, displacement diagram, we haven't looked at this yet. The displacement diagram, if we look at on the next page, 227, this is the, if you would, the end of the problem where they plotted the displacement diagram. We're not going to actually make this picture, but we are going to identify, and we're going to break this down so that we can find our betas for each one of our time intervals and kind of see how this works. Because you will be plotting some for your assignment, but you're not going to be plotting this one. So a displacement diagram is basically going to give us a graphical picture of what's happening with displacement per degree of cam revolutions, okay? So along the x-axis here, this is going to be displacement, or this is going to be, I'm sorry, the cam rotation in degrees. So you're going to notice that right along this axis, you're seeing 90 degrees, 180, 270, and 360, and then a couple other milestones in between, okay? Then you're going to notice that right underneath there, they identify beta 1, beta 2, beta 3, beta 4, and beta 5, okay? Each one of those betas are how many degrees it takes of that revolution to do the prescribed motion for that step. So beta 1 is going to be how many degrees does it take to go my first step, which is a rise of 2 inches in 1.2 seconds. Okay, how many degrees does that take? The second beta is going to be, all right, how many degrees am I going to dwell or stay in the same place? Then the next one and the next one. So I want to be able to figure out individually how many degrees of that 360 do each one of those take. Okay, that's what the betas are, and we're going to be calculating those in just a bit. Now, the other things that you see down here are going to be the corresponding time. Notice that on the bottom here, this is how much total time it takes to do one revolution. So we start out at a time of 0, and you'll notice that in line with 360 degrees is the 3.9 seconds. That was the total amount of time for one revolution, right? So then you're going to notice underneath here that T1, T2, 3, 4, and 5 are all going to be corresponding to the time for each one of those steps. So T1, for instance, is going to be the 1.2 seconds. So you're going to notice here that from 0 to 1.2 seconds is where our T1 time is. Then T2 is going to be the difference between 1.2 and 0.5. So it should be, yep, 0.3 is how much we dwell for, and so on as we go. So this is going to be a diagram that we are going to be creating. So that's the x-axis. The y-axis is going to be the follower displacement. So this is going to be the rise, the dwell, and the fall, if you would. So your maximum number on follower displacement is going to be the maximum displacement that we end up seeing. So when we look back at our displacement or our motion sequence, you're going to notice that in step number 1, we rise 2 inches, okay? And then we dwell, and then we fall 1, and we fall another. Our total rises have to equal our total falls, okay? So if I rise up 2 inches, that means that per that 1 revolution, I have to get back down a total of 2 inches. So you're going to notice that I fall 1 and I fall 1. So my falls equal my total rise. You can break your rise into different steps if you wanted to, all right? And you can break your falls, as we see here, into different steps. You don't have to do all the rise in one and all the fall in another single step, okay? So you just have to figure out how many rises do I have and what is the total rise, and then making sure that your falls are going to be equal. And you'll see that in what you do. So over on our displacement diagram, notice that my maximum value is going to be my highest value for the amount that I'm going to displace in terms of the rise, okay? So that's going to be the 2 inches. So in my first sequence here, from 0 to what we're going to find to be 110 degrees, 10.5 degrees or so, I am going to rise a total of 2 inches. So going from my 0 all the way up to here, that's going to be my maximum rise, okay? Then you're going to notice that for the next sequence, it's just going to be a straight line. That's called a dwell. That means that I'm not going to rise or fall. I'm just going to stay in that one spot. And so it's just going to be a straight line for however long that dwell is. That's going to be the next time interval. Then you're going to notice that I'm going to fall 1 inch, right? See how graphically that's in line. I'm going to fall 1 inch in the amount of time, the T3. And then you're going to notice that I dwell again, straight line, for however long that is. And then lastly, I'm going to fall then back down to my baseline, or back down to 0, if you would, for the rest of the time that's there. And then technically my 360 and my 0 are really the same point. I start right back over on my next revolution and go through that same sequence again. Okay. Now you're going to be plotting the displacement diagram. Now, something we didn't do here yet that they did in step number 3 is we want to figure out how many degrees are taken up of cam rotation for each one of our sequences of the motion. Okay, so that's what we're going to do next. I just wanted to make sure that you understood what the diagram was here. So we're going to calculate what our betas are. Okay, so again, our betas are going to be how many degrees of motion, or how many degrees of rotation does that motion take up. So if I go back underneath here, my step number 3 is going to be determine the cam rotation for each one of the follower intervals. So step number 3, okay, I'm going to calculate out what is my beta 1, right? My beta 1 is going to be calculated using the angular velocity of my cam, okay, times the corresponding t, okay? And actually, because it's beta 1, it would be t1, all right? Now, if I look at the time for sequence for the step number 1, if I go back over here, my T1 was 1.2 seconds, right? 1.2 seconds. So I know that this is going to be in seconds. And my cam W, I reported it. Its final answer was in RPMs, but I'm actually going to use this value right here, revolutions per second, down in here, because this is going to be in seconds, because I just want to know how many degrees is that going to be. So my beta 1 is going to be equal to 0.2564 revolutions per second. Make sure you put the units in there. Multiplied by T1, which is 1.2 seconds. Because we're multiplying these together on top, my seconds cancel with the seconds on the bottom. All right. And then my beta one comes out to be, what do you get if I multiply those two together? And Tyler got, yep, he got the same thing I did, 0.3077. And this is going to be revolutions. Now, that's not degrees yet. Remember, beta is degrees. How many degrees of rotation do we have? So it's telling us that we're about a little bit shy of a third of a revolution, right? So now we need to convert this to degrees. How many degrees are in one revolution? Yep, 360 degrees, right? So that means that my beta one then is going to be equal to pi by 360. What do we get for degrees? How many degrees of revolution? Hundred and 110.7, 110.76. Yep. 110.76 degrees. Okay. So we always want to get the betas into degrees. So this is our first one. Okay. Let's do our next one. We want to do beta 2. Okay. Beta 2 is going to be the same equation, but this time we're going to do T2. All right. So beta 2 is going to be 0.2564 revolutions per second time. This time, our T2 is going to be 0.3 seconds. Seconds cancel, and our beta 2 should come up with 0.077 revolutions. And then we're going to convert that 360 degrees in one revolution. Revolutions cancel top to bottom here. So we should end up with about 27.6 degrees is equal to beta 2. Everybody get that? Now go ahead using the same format, determine your beta 3, 4, and 5. Okay, write them out, and then we can compare. Or you can look, you can just make sure that at the top of page 127 that your answers are the same. If you're off by a decimal or so, I'm certain that it's going to be a little bit of rounding, but you should be, relatively close. Like my beta 3 came out to 83.07. They had 82.9. Okay. Way close enough because we can hold more decimal places on our calculators and such. So I know that they always round to 3 significant digits pretty consistently throughout their calculations. So any questions on the last three betas here? Once we get those values, and again, should be matching pretty closely to what the book has. All right. And then again, those corresponding betas are going to be the values that we see down here along the axis. Now, you are going to be creating a displacement diagram for the problems that you do for two of the four problems. You're going to be going through this process and doing all the labeling. So this is the displacement diagram that you're looking at, okay? Now, you are going to be creating these in AutoCAD, all right? So because they are going to be to scale, you're not going to be just sketching them. That's not what we're doing. We're going to be creating them in AutoCAD. We can get a nice, accurate version here. Now, constructing the radiuses in and out, we'll talk about that in a little bit. That's based on the motion scheme for each one of those steps, okay? But as we look at the x-axis here, do you see where your betas would be for each one of those values? So it's a total of 360 degrees. And then to scale, you would have each one of those values. So the first one was 110.5. Our next one was about 27.6, 82.3, then 55.3, and that 80, about 83, 82, 83 is going to be the last. When you add each one of those up, they should come out to be 360 degrees. Okay, if they don't, that's a great check for you to do. Then you did something not quite right. Now, another thing that we see here, something I'm going to repeat a couple times, but I'm going to say it the first time here. When you determine how long this axis is going to be, don't try to tie it to 360. So don't try to make this 36 inches long. If this is only 2, you're going to have a really long x-axis and a really short y-axis, and then it's not going to come out correctly. Okay, it's not going to look right. What you want to do is you want to look at whatever your y-axis is. So for instance, this is a total height of 2 inches. Okay, I want to have everybody's attention quick on this. Notice that you have a height of 2 inches. What you want to do is you want to make your axis about 3 times whatever that height is. So in this case, if it's 2 inches, you want to make your x-axis 6 inches long. And then just divide that by 360 to know how much of that 6 inches is going to be a single degree. Does that make sense to everybody? And then you mark off however many degrees. So then you would take whatever it is per degree, however many inches that is, and you would multiply by each one of your betas to get each one of those lengths. Okay. All right. And I know when you do the construction, I am not this time, we're in the 7th week. You guys have been using AutoCAD a lot. I'm going to be in this particular chapter kind of guiding you through the construction, and you're going to see it in the book, the steps to do it. I'm not going to demonstrate AutoCAD here. I'm going to let you guys kind of figure that out. Okay. These are the types of things that especially when you get out in industry, you're not going to have somebody showing you how to do all the steps all the time. You're going to have to kind of, look at it and be like, and I know with the CAD skills that you have, you'll be fine. You'll be fine. And I'll kind of give you some hints along the way, but I'm not going to be drawing this out in AutoCAD this time. You're going to basically be seeing what you see here and then translating it over. So for this problem 9.1, we are going to be leaving this. Again, we're not going to generate the displacement diagram. I wanted to show you where the betas, how it's constructed on the x-axis, the y-axis, so that as we, get closer to doing that, you'll be able to do it because we need to know a little bit more about follower motion. Okay, so any questions right now on 9.1? So what you'll be handing in are basically the first 3 steps. So step number 1 was the total time. Step number 2, which was one of the things they were asking us for, is our cam rotation speed. And then each one of the betas 1 through 5. Okay, calculating each one of those. All right, so the next section that we have here is we're going to be looking at follower motion schemes. So I'm going to go back to our PowerPoint presentation. And we already looked at displacement diagrams kind of in detail, but a displacement diagram, just in reviewing what we had looked at previously, it represents the motion required in terms of distance along that vertical axis versus the angular displacement along the x-axis, or that horizontal axis. So along the x-axis is one rotation, or 360 degrees, and on the y-axis is what the travel is that we're going to be having. Displacement diagrams give us that graphical representation of the motion that will be used to generate that profile of the cam. So we need a displacement diagram before we can even generate the profile of the cam itself. Okay, so we have to have a good one of those. And it says they must be drawn to scale. Must be drawn to scale. So that's why we're going to be using AutoCAD for those. Now let's look at different follower motion schemes. Okay, there's a lot of different motion schemes that are available for the follower. Okay, so the objective of these schemes is to produce the movement of the follower that is going to be nice and smooth. Okay, and that means kind of being aware of the accelerations that we have. So slow moving cams mean that you can use high accelerations because they are not going to adversely affect the motion. And we'll talk about that in a little bit. But when we have high speed applications, now we need to be more aware of being a little bit more smooth in and out with those accelerations so that we minimize vibration and we ensure that we keep the follower in contact with the actual cam itself. That's really important because if it's not in contact with the profile of the cam, then it's not imparting the motion that we need. Okay, so that is key in every one of these situations. In some cases, we might be able to use gravity, you know, depending on the type of the follower that we have. But most often, we probably have some sort of a mechanism like a spring that is making sure that it's always in contact and has some, you know, positive contact. So follower motion schemes, there's some things that we, like terms and things that we need to know as we go into this. So let's go underneath the book here. So on page 227, the section here, follower schemes. And then here are some of the terms and the variables that we're going to be dealing with. And here gives, in some cases, a little bit more information on each one of them. So I listed them briefly in the PowerPoint presentation, but here are the full explanations for each. So number one, H, this is going to be the total displacement, whether it is rise and or fall, but it's going to be the total height or the total displacement in an interval. The next one is T, is going to be whatever the time period is for a rise, fall, or a dwell. The lowercase t is going to be the time into the rise or the fall interval that defines the instantaneous follower properties. Beta is going to be the rotational angle of the cam for any particular motion that we're looking at. And we already looked at the capital T's and the betas here. Now, this is going to be phi, which is an angle into the rise or fall interval that defines maybe an instantaneous follower property. And then we've got our W, our cam, the speed of our cam in degrees per time. Now, if we're reporting it to determine what is the rotational speed of the shaft that we need to, you know, have this going at to get the rotation or the motion that we need, it's usually going to be in RPMs. But if we're looking at in using it to calculate our betas, then it's going to be revolutions per second. Okay. And then lastly, it's going to be our total R. That's going to be the magnitude of the instantaneous follower displacement at any given amount of time, like looking at a smaller increment of time. Now, as we look at the types of displacement, let me go down here. Oh, V is going to be follower velocity, and then A is going to be acceleration. So those are kind of common. Now, the motion schemes themselves, the first one that we're going to look at is going to be constant velocity. Okay, then we're going to look at constant acceleration, and then harmonic and cycloidal. So let's take a peek back underneath our book here. So on page 228, page 228, in the first column, it goes into detail about constant velocity motion. Then it goes into detail about constant acceleration, then harmonic motion. And then lastly, at the bottom of page 230 and on to page 231, it's going to talk about cycloidal. Those are the four types of motion that we're going to encounter in this chapter, okay, or in our analysis and in our design. Now, the first one, constant velocity. Let's look at this one first. So if we look at constant velocity, Again, it talks about it here. It's the most simplistic that we have. And if we look on page 229, the first column here at the top, this is constant velocity. The first part here is going to give us what our follower displacement is and what the profile of the line looks like. It's the easiest one to construct. So we're going to go from wherever we start, we're just going to draw a straight line up to wherever we end. So for instance, if we go back to the displacement diagram from what we saw earlier, it would be taking this dotted line and a constant velocity. If we were using this motion sequence, it would just be going from the start of that motion to the very end of it. Done. Okay, straight line. Now, this isn't used very often for the reasons we're going to see here. Number one, constant velocity means that from the get-go, we're going that fast right away. It's kind of impractical to expect that because most often we got to speed up to something before we get to its highest speed. So in theory, constant velocity is not something that is really even achievable, okay? But if we do turn on something and turn it off suddenly, it has to be low speed, okay? Otherwise, we are going to create a lot of jerkiness and the potential of having our follower not be in contact with our cam, which is something we can't have. So again, very simplistic, but yet again, reserved for very low speeds. The other part of this is the acceleration curve. So the first curve is going to be our displacement. Then there's our velocity, just turning it on and off. Because it's constant velocity, it kind of means that there isn't, any acceleration, but yet because of the nature of how this works, you actually get an infinite amount of acceleration like on the get-go because we've got to get up to the velocity really quickly. And then we have to shut it down really quickly. So we get these spikes on the ends, which is not something that we want. And again, it is only reserved for low speed and actually almost used never. Okay. But it is a type of motion sequence. The next one that we have is going to be constant acceleration. We need to turn the page for this one. Constant acceleration has a benefit in that you're going to notice that instead of a straight line here, we have a little bit of a curve going in and out. This is going to help us because now what we have is we have a ramping up to the maximum velocity as we speed up, and then we have a ramping down as we, stop that sequence. So there is a gradual in and a gradual out, okay? And then you're going to notice here that our acceleration still is pretty abrupt on the in and the out, but it's not infinite in either direction. So there is an improvement there on both the transitions in and out. Again, this would be relatively low speed, higher speed than the constant velocity, but we're not going to want to use it for anything that is, a significant RPMs. All right. The last two are harmonic and cycloidal. Those are going to be the two that we see most often. And here again, you're going to notice, although it might not look very different from what the constant acceleration is, you're going to see a ramping in and out. And then we're also seeing more of a curve as we get up to our maximum velocities. And then we also, again, are seeing more of that curving in and out on the accelerations. So because of that, we have smoother motions, and what's going to occur less is we're going to have, fewer points where we're going to have jams and or non-contact with our cam itself. Okay. The last type, which is the smoothest of all and can be used for the high-speed applications, is going to be cycloidal. Cycloidal is at the top of page 233. And sometimes, again, the displacement doesn't look very different, but now we're getting curves in and out on both the velocity and the acceleration. And that's where we're now ensuring that indeed we're going to have constant contact. And when we're at the higher speeds, we're not going to have issues with jamming or vibrations. Okay. So two that we're going to focus most on are going to be the harmonic and the cycloidal. Okay. Now, once we identify which one we're going to use, okay, or you get in your problems which ones you're going to be using, now it's how to construct them. Okay. So when we look at harmonic construction, okay, it is going to be on our displacement diagram at the top of page 232. Okay, at the top of page 232. Now, as we look here, you're going to notice that our vertical axis, which is going to be, as we know, the displacement that we have for any single step. So for the case, for instance, that we were looking at an example 9.1, this is, for instance, 2 inches. This is then going to be a diameter circle, if you would, of 2 inches, where at the midpoint, this is going to be 1 inch going up and 1 inch going down. So this half circle right here is going to be a diameter of 2 inches. Does that make sense? So you physically are going to make that to scale. Then what you're going to do, depending on how far, this is your beta or your time, okay? You're going to know how far that's going to be, like how many degrees along my 1 revolution, my 360 degrees is that? And now I'm going to draw that out, okay, to scale. Now I'm going to repeat again. We go back to that original diagram, okay? The total length here is going to be 3 times whatever your height is. So like I said earlier, since this is 2 inches, this is going to be 6 inches along here. Okay, total of 6 inches. So now if we know how long this section is right here, we know that it's 110.5 degrees. Okay, we need to say, okay, if this is 6 inches along here, how much is that? If 6 inches is 360 degrees, how much is it per degree? And then you're going to multiply that by 110.5 to get what that distance is. Does that make sense to everybody? Okay. And yours is going to be a little different. But what I don't want to see, and I'm going to repeat this again, I don't want you to make this axis super long. Look at how high your maximum value is here, multiply it by 3, and that's how long this axis is going to be. You are not going to get even increments. You're not going to be like 1 inch is equal to 1 degree. That's going to be 360 inches along. That's not going to make sense. Does that make sense? Does that make sense? Okay. So keep that in mind, that you're going to have to kind of do that conversion. So now what you do is so for instance, if we're looking at just this chunk right here, we've got a half circle equal to 2 inches. We're going to break it into, back up here, page 232, we're going to break it into 6 equal parts. Okay. So if we look here, this is going to be my 0 is going to start down here. Then I'm going to have 1, 2, 3, 4, 5, 6. And if we look, that's 1, 2, 3, 4, 5, 6 sections. I have 180 degrees. How many degrees are between each one of these sections? If I take 180 divided by 6, what do I get? 30 degrees. So from the center here, this is going to be a 30-degree angle from here, from here, from here, and in between each one. And then starting at the bottom, here's my 0, 1, 2, 3, 4, 5, 6. And we just number those 1 through 6. Okay. Now, once I have those figured out, and I know how long this part of my motion is, wherever it's ending, not the full length, but wherever it's ending, I am now going to take whatever that distance was, and I'm going to divide it into 6 equal segments. Do you see that? And now that is just going to simply go up. All right. And where it intersects with its corresponding number over here horizontally is where that point is going to be. And then number 2, number 3, number 4. So what you want to do is you want to duplicate the construction that we see here for harmonic motion. Okay. Now, let me ask you this. Once I have the points in place, here's 0, 1, 2, 3, 4, 5, and 6. How am I going to connect those so that they look nice? Am I going to put a straight line in between each one in AutoCAD? Say no. Because it doesn't look straight here, does it? It's a curved line. So what type of a line am I going to put through those points?
They call it a spline.
They do call it a spline. Yes. So you're going to have to find where spline is in AutoCAD. If you go underneath where the line is, there's like an arrow down, and then there's extras down underneath. Yeah. Polyline. Yeah, it would be a spline, Emily. Yes. But on that same order. And it's going to be a spline through points. Okay. Because you want to hit each one of those points, and then it's going to make a nice curve along that. Okay. And most of you did, and maybe not every person, but if you had me for computer programming, we use that function in there. All right. So yeah. So that's how you would do that. And then you would continue on. So for instance, if we're using harmonic motion for that first segment, okay, it would only be for this part that we would do that construction. So for instance, you would have your half circle divided into 6, then this part right here would be divided into 6, and then you would have your horizontals, your verticals, find the lines and do your best fit, not your best fit, I think it's called fit to spline or something like that, through points or something like that, okay? And then your next section, whenever there's a dwell, all it's going to be is a straight line. Okay, that just means that it's staying in the same spot, okay, for that many degrees. So a dwell is just going to be a straight line. Then if we would have a fall, we would do that same thing where in this case, it would start here and it would end here. And then we would do a half circle, which is going to be then a diameter of whatever that fall would be. I think in this case, it was 1 inch, okay? So again, we would then break it into its 1, 2, 3, 4, 5, 6, go over. This would break into 6 equal segments, and we would find the lines and then do our spline fit spline or spline fit through the points or something like that. Then we've got another dwell, and then we would have one more fall over here. Now, in this case, you might be like, wow, that one and that one are the same size. Their radius would be the same size, okay, going around, but their time is different. So you can't take this and copy it down here, for instance, okay? You would, because the time is spread out over a different amount, this is going to be broken into your 6 equal segments. So that's going to change the length of that curve. Okay, so be careful with that. If even though the fall is the same value, the radius of your circles can be the same. You could copy this down, but the placement of the points is going to be different horizontally. Okay. So that's how you would construct harmonic. Okay. Let's look at constructing cycloidal. Okay. Constructing cycloidal. On page 233 at the very bottom here, this one looks a little bit different. Okay. You'll notice that here we're still using the 6 equal parts. So once we know what our beta is, right, or our total time, that section we're going to break into 6 equal parts. All right. But now we're not doing the half circle on the y-axis. We are constructing a complete circle, and its radius is going to be this equation right here. Okay. It's going to be the height. So whether that is a fall or a rise does not matter. So whatever is the height that you need to go. So for instance, in this case, it would be whatever this distance would be for the total time that you need to be at. So it would be this value right here. You're going to take that height, you're going to divide by 2, and you're going to divide by pi. And that will be the radius for that circle. Okay. Notice how this circle is placed. This circle is placed, if we go to the end of our motion, we go down, down, down through the middle, through the origin, and we extend that line. Our radius center is on that line right there for that circle. Does that make sense, everybody? You see that? Okay. And then what's going to happen is you have this broken into 6 equal segments. This time it's going to be 60 degrees between. You're going to start at 0 and you're going to go around counterclockwise 1, 2, 3, 4, 5. Okay. Then notice what happens here. For 0, 6, and 3, they come together in the middle. So here is where it's going to cross 0. Here is where it's going to cross 3. And here is where it's going to cross 6. Okay. Now, if we pull across and we find where 4 and 5, where those two come together, this is going to go all the way up to 4 and to 5. And then at the bottom, this is going to be where 1 and 2 come together at the center. That is going to come to 1 and 2. And notice that these lines are parallel to one another. So in AutoCAD, you can create those really nice and accurately. Okay. So this is going to be your guide for the construction for cycloidal motion. Okay. Now the last, let me take a peek at the end of the chapter here. I know which problems I'm having you guys do this for. So homework, I just want to be sure. Harmonic motion, good. And cycloidal. Those are the only two. So harmonic and cycloidal are going to be your homework problems. Okay. If you are interested, here is the constant acceleration construction. Okay. And again, you won't have this as an assignment, but this is just a little bit different. And then the last one is the constant velocity, which, I mean, really, there's no construction. It's just going to be from 0 to whatever the endpoint is as a straight line. Like, that's all that it is. All right. So those are the four main types of, um, what is it called? You gotta go back to the beginning of the chapter. Follower motion schemes. Follower motion schemes. All right. So let's catch ourselves up on our PowerPoint. We talked about constant acceleration, constant velocity, harmonic and cycloidal, most popular. And then we've got two examples in our book here where we're going to be looking at creating the construction for these motion schemes. So if we go to page 234, we're going to be looking at our first example, or it should really say our second example, but the first of for this section is going to be example problem 9.2. And again, we're going to do steps 1 through 3, okay? And then we're gonna finish it with the construction in CAD. I'm not going to do the CAD demonstration, but it would be done to plot it in CAD. So let me go underneath our camera. So problem 9 or example problem 9.2 is going to be at the top of page 234. It says we have a cam is to be designed for an automated part loader as shown down here. Okay, using the motion equations, construct the chart that tabulates the follower displacement versus the time. You are not going to be doing that, okay? And what that is it would be using Excel to create this. What we're going to actually do is create the displacement diagram using the graphical means that we've just looked at, okay? And then it just says here, and plot the data with the subscribed motion as we see here in 1 through 4. So this is telling us that we are going to have a rise of 50 millimeters in 1.5 seconds using constant velocity motion. Okay, so that's just going to be the straight line. So we'll be using that. Then we want to return in 2 inches, or I'm sorry, in 2 seconds using cycloidal motion. So that what it means is we're going to do a full fall or a return of the 50 millimeters, but this time we're going to take 2 seconds and we're going to use cycloidal motion to do that. Then we're going to dwell for 0.75 seconds and then we're going to repeat. So really our motion is only the first 3 steps here. Okay. So first things first, we're going to first calculate what is the total time in that cycle. We're going to calculate our betas. And we're going to calculate the rotational speed of that cam. And then we'll look at how we would actually construct the displacement diagram. So example 9.2, okay? And step number 1 is going to be the total time. So we want to take and we want to find the total time for 1 revolution or 1 cycle. And that is going to be T1 plus T2 and plus T3. Okay, and these are the times in seconds. So our T1 is going to be the 1.5 in step number 1. So 1.5 seconds plus T2, which is going to be 2 seconds, plus T3, which is going to be 0.75 seconds. So what is our total time for 1 revolution? $4.25, that looks and sounds correct to me. 4.25 seconds. That's going to be I'm not going to put a box around. That's our total time. Okay. I might put seconds. Just because sometimes a 5 can look like an S and we want to be sure we know which one is our units. So step number 2 here is going to be calculating or determining what is the rotational speed of the cam. Okay. So that means that that's W of our cam, right? And that's going to be 1 revolution divided by the total time to accomplish the the three steps of our motion. Okay. So we're going to say, all right, 1 revolution divided by 4.25 seconds, right? So the W of our cam, what do we get? Five one. Is that right? 5.3. Yep, that's what I got too. Okay. And that's going to be revolutions per second, right? Now, if we report this to the world, right? And we want to know how fast does our shaft have to go around, we want to convert that to RPMs. So we're going to say 60 seconds in 1 minute. Okay. So our W of our cam officially, seconds are going to be canceled out here. What do we get for our angular velocity of our cam in RPMs? 14.112. Okay. And that's going to be RPMs, right? So this would be when they ask us for the speed of the cam, that is going to be the value that we want to report in RPMs, not in revolutions per second. Okay. Now we've got 3 steps in our motion here. So we want to figure out what is the angle that each one of those motions takes up in our, revolutions. So step number 3 is going to be calculating our betas, right? So beta 1 is going to be equal to our W of our cam times our T1 in this case, right? T1. Now we know that our T1 is in seconds from above, right? So that means when we use this angular velocity of our cam, we cannot use RPMs. Okay, we need to use the revolutions per second. So we want to use the 0.2353. And that's going to be revolutions per second times 1.5 seconds. So the seconds cancel out here. And our beta 1, how many revolutions is that going to be? You get 0.353 revolutions. Please be checking this. Okay. Make sure you're checking it on your own calculators. Now, we want to know how many degrees this is. So we need to convert this 1 revolution into 360 degrees. So revolutions cancel out. You should get 127.1. Okay. All right, then we have 2 more, beta 2 and beta 3. So go ahead and calculate beta 2 and beta 3. A good thing to do after you get your three values, just add them all three up to be sure that you indeed get 360 degrees. Okay, and I did for each one of mine. So hopefully you got. Do you want to show it? Do you have to? I don't think so, but if you find that you're having any problems and you didn't check it, this is a good place to, just make sure. It's also a good idea, like maybe you missed a beta on accident and all of a sudden there's a gap and you're like, oh crap, I'm not getting my numbers. I mean, if they're within a half a degree or something like that, but if they're more than 1 degree, I would think that you're missing something. So yeah, I want to see it. I think it's a good idea. There's not a reason not to do it, is there?
Well, of course you can do it. Show.
All right, everybody do okay on that part? Okay, so now we know what our time frames are for each one of our steps along the motion. So if we look here, that's really the end of problem or example problem 9.2. Now I believe 9.3, yep, and it is, 9.3 is actually creating the displacement diagram. And let's see how they do this. Again, I'm not going to demonstrate this in CAD, all right, but I want to make sure that you know how you're going to do it. Now, for example 9.3, it says here you want to make the displacement diagram. I'm not going to have you draw this, all right? You don't have to draw this. We're going to walk through it step by step here. That's why I expect that you're paying attention. But what you do have to do is you have to show me the calculation for the radius of the circle to do the cycloidal motion. So we'll look at that in just a bit. So if we go back to the problem statement for the previous example, it said that we're going to rise 50 millimeters in 1.5 seconds, and it's going to be constant velocity, okay? So if we go back to creating this, you're going to notice that the beta along the x-axis, this total beta, this total number of degrees here along the time is going to be 360 degrees. So here's our beta 1, our beta 2, and our beta 3. So this line right here is that first motion, and we're going to rise 50 millimeters, all right? So remember, when you're creating your displacement diagram, this is going to be a total of 50 millimeters high. How long will the total axis along the x-axis be then? What did I tell you?
So 150.
3 times, yes. So 150, exactly, Tyler. So 50, 50, 50, all the way along. Now, you're going to take 150 and you're going to divide by 360 to get how many millimeters, if you would, are per degree, right? Then per degree, you're going to know how many. And now you're going to take whatever your beta 2 or your beta 1 is, 127, you're going to multiply it by that value. Does that make sense that you can get your distance along here? Okay. Now, again, I'm not demonstrating that. You guys are AutoCAD experts at this point, right? So now that you know how far this is, and this is constant velocity, how you construct this is you just start from 0 straight line all the way up to the top. That's it. Okay, it's that easy. All right, no construction here. Then immediately after that, you're going to go into your cycloidal motion for the fall. Okay, now the cycloidal motion has to occur, I think that was in 2 seconds, which is going to then be, in this case, 169.3 degrees. And again, from this spot over this section right here is going to be just the cycloidal from here to here. So now you're going to take however many millimeters are in 1 degree, multiply that by 169.3, and that'll be the length that this is, okay? Now what you're going to do is you're going to divide that total length into 6 parts. So this is going to be your, let's see here, this is going to be your 1, 2, 3, 4, 5, and 6. No, sorry. That's going to be your 0. This is going to be 6, 5, 4, 3, 2, and 1. And then this is 0 here. Sorry. Yeah. Okay. 3, 2, 1. There you go. So now down here, our cycloidal motion, the radius of that circle is this equation right here. Okay. So if we look, example The only thing you need to show me here is this equation. Example 9.3. Our radius for our cycloidal motion is going to be h1 divided by 2 pi. Okay. Now, that is going to be our 50 millimeters. That's the height of the rise in this case, the fall as well. 50 millimeters divided by 2 times pi. So what does your radius come out to be? Hopefully 7.96 millimeters. Okay. Now that is the radius of that circle. Okay. And we're going to look at now the construction of that circle. All right. The construction of the circle is going to be down here. All right. It's coming on the fall, if you would. You're going to start at the end point and you're going to go straight down to that origin down there. That's going to be the line you're going to extend for the center line that has a radius of 7.96 or about 16 millimeters in diameter, right? Not quite. That's going to be where the center is. Then what you're going to do is you're going to break this into 6 equal segments. The top 2 are going to be 4 and 5. The bottom 2 are going to be 1 and 2. And then the middle is going to be 0, 6, and 3. Okay. So down the middle is going to intersect with 0, 3, and 6. And then the bottom 2 are going to be 2 and 3. Sorry, 1 and 2. You can see the numbers there, 1 and 2. And then the top ones are going to be 4 and 5. Okay. Now, how far this is away here, it's random. It just needs to be out of the way. So you want it down below the surface, like whatever that horizontal axis would be. Okay, that's all. And then you're going to put a spline through those points, and that's going to then be the curve that you create. And then the last part of this, the last beta, is going to be the dwell. So that's just going to be a straight line for whatever equates to the 0.75 seconds, however many degrees that was, 63.7 degrees. Okay. Questions. Now on a displacement diagram, what are you going to label? Okay. You are going to label and make it just like, this is the best displacement diagram they have. Example 9.1. Okay, example 9.1. So here is your x-axis, here is your y-axis. Make sure that you're going to be putting in your scale. Make sure that you put units and yet you identify this. So all the labels that you see here are the ones that you're going to add as far as the x and the y-axis. This is the total cam rotation in degrees. Here are kind of the milestone degrees. Then you have your beta 1, 2, 3, 4, and 5. Okay. And then your times, corresponding as well. So there are quite a few labels for this. All right. Now, construction wise, do you have to show all of the construction? What I'm going to leave you with on that is, for instance, on something like this, it might get a little crazy. Okay, because you're going over the lines and up, and then you've got some other indicators. What I do want to see are your points along here, so I can see that you put points in there and that you have them going in and out. I do like to see this construction too, but if it interferes with things, then you can take it off, especially if they're on the other side and you're falling. The one that you can do that doesn't interfere is going to be the cycloidal. So if you have a cycloidal motion, I think it's doable to add it and put it in there and show the construction for that one, because I don't think it interferes too much. Okay, I'll let you be the judge. Let you be the judge. Okay, so let's look at the homework assignment that you can do to this point. You can do the first 2 of the 4 problems for this assignment with what we had talked about today. So on page 254, your homework assignment, the 2 problems that you can do are going to be 9.7 and 9.9. 9.7 is you have a cam drive is used as a mechanism that tests the durability of oven doors. The cam follower must rise outward in 2 inches with harmonic motion in 1 second. It's going to then dwell for a half a second, and then it's going to fall the full 2 inches using harmonic motion again in 1 second. Then it's going to dwell for another second and then repeat the sequence. Okay. So in this case, there's 1, 2, 3, 4 steps, including both dwells and both the rise and the fall. And then it says, determine the required speed of the cam. That's going to be that W of the cam, and graphically plot the follower displacement diagram. Okay. So you're going to have to calculate your betas and then plot all of those. And then you're going to be drawing this on AutoCAD. Okay. The second problem that you have is 9.9. You have a cam drive is used for a mechanism that packs stuffing into shipping boxes. The cam follower must rise outward in 1 inch with cycloidal motion in 1.5 seconds. Then it's going to fall 1 inch with cycloidal motion in 1 second, and then it's going to dwell a half a second, and then it's going to repeat it. So in this case, you're going to have 1, 2, 3 motions, including the dwell, okay, before you repeat it. Determine the required speed of the cam and graphically plot the follower displacement diagram. Okay. Now, if we look at these two, so I'm going to kind of give you a hint here. So for this first one, the cam follower must rise 2 inches harmonic motion in 1 second. Okay. It's going to dwell, and then it's going to fall 2 inches harmonic motion in 1 second. When you construct this the first time on the rise, do you see how the fall would be the mirror because the time is the same and it's the same sequence of motion or the same motion scheme? You could mirror that one, all right? But the second one you cannot. So the cycloidal motion down here, even though it's the same rise and fall, the time is different. So the first cycloidal motion is in 1.5 seconds, and the second cycloidal is in 1 second. So the horizontal distance is going to be different on each one of those. So the size of the circle will be the same because the fall and the rise are the same value. So when you calculate the radius, that will be the same for each. So you could copy that circle over to the fall, but it's going to be over shorter distance. So it's going to be a different horizontal. So your values in and out, your radiuses are going to be different. Okay, so that one you can't mirror or use again, if you would. Does that make sense, everybody? Okay, now I did not demonstrate this in AutoCAD, but you need to do it in AutoCAD, all right? Because it's going to be more accurate, really for the sake of time, you know, and kind of explaining it. And I am confident that with your AutoCAD skills and your ability to kind of go through here and see how things are constructed, I'm confident that you can translate that over. But if you have any questions as you're working, that's what I'm here for during our lab time. So I'm going to stop our recording at this time.